Welcome back for some more chemistry. Today's topic is called Lewis structures. The purpose of making a Lewis structure is to show how atoms share electrons in order to become more stable. So in this lesson, you're going to be watching me do a little bit of whiteboarding, and I'm going to ask you to do a couple of things. The first thing you need to do is look at the formula of the molecule, and I want you to add up all of the valence electrons. We're then going to arrange the atoms in a symmetrical fashion. And we're going to distribute the electrons in a way that shows how the atoms covalently bond. When atoms covalently bond, they share electrons. I will bring up three different types of bonds. The first is called a single bond. In a single bond, two atoms share two electrons. In a double bond, two atoms share 4 electrons. And in a triple bond, two atoms share 6 electrons. So let's get started. The first molecule that I'm going to use as an example is something everyone's very familiar with, and that's water, H2O. To draw a Lewis structure, the first thing you need to do is add up all the valence electrons in the atoms in that molecule. So I hope you know your trends. For instance, in a hydrogen atom, there's one valence electron. Now, we have two hydrogens, so we're going to show this as 1 plus 1. And then an oxygen atom has 6 valence electrons. I want you to add those up. Now we're going to draw the molecule. Sometimes students ask me, how do I know which atom to put in the middle? Well, here's a suggestion for you. A hydrogen atom starts off with 1 valence electron, but it only needs 1 more to be stable. So a total of 2, right? The reason for that is it's going from a 1s1 electron configuration, and by gaining 1, it turns into a 1s2 electron configuration, which matches that of helium, which is a stable atom. So if hydrogen only needs to gain 1 more electron, he really only needs to bond 1 time, which means your hydrogen atoms should always go on the outsides of the molecules, never a central atom. The other atoms that we're looking at, though, are all trying to achieve what we call a valence octet. In other words, 8 valence electrons. There's another rule of thumb. If you have several different elements in your molecule, then typically the atom that goes in the middle is the least electronegative out of all the atoms. So if you're in a situation like that, try to keep that rule in mind. Put the least electronegative element in the middle. In our scenario, we're going to put oxygen in the middle. And we're going to put hydrogens on the outsides because we know they only bond once. Your job now is to start placing electrons where you believe there are covalent bonds, where they're going to share the electrons. For instance, between this hydrogen and this oxygen, let's have them share 2 electrons. So there's 2 of our 8. On the other side, let's create another covalent bond. So right now you'll notice this hydrogen has 2, and this hydrogen has 2 valence electrons. So they're stable. But we've only used 4 of the 8 that we have to work with. Where could we possibly put the other 4? It looks like the hydrogens don't need any more, so we really can't put them in a bond. So your other option is to put them around the atom, and these are called lone pairs. Lone pairs are electrons that are not involved in bonding. Now later on, we will learn that they will affect the shape of a molecule. For now, we're simply focused on the stability of the atoms. So I'm going to take those other 4 electrons, and I'm going to put 2 on the top, and I'm going to put 2 on the bottom. And now you'll notice I've used all 8 of the valence electrons that I had to work with. So now we step back and decide, does each atom have what it needs to be stable? This hydrogen has 2. This hydrogen has 2. Awesome. And if you look around the oxygen, it has a total of 8. And so we've created A very good Lewis structure. Throughout the remainder of the video, you'll be watching me draw molecules. I'll be whiteboarding, and I hope you'll be practicing along with me. We'll be focusing in on single bonds, double bonds, and triple bonds. Good luck!
Let's begin drawing some Lewis structures. The first molecule that I'd like to draw is CH4. The first thing I want you to do is add up all the valence electrons that are in this molecule. Carbon has 4 valence electrons, and each hydrogen should have 1 valence electron. So if we add this up, it's a total of 8 valence electrons to work with. Now let's arrange the atoms symmetrically. We're going to put carbon in the middle and hydrogens on the outside. We have 8 valence electrons to work with. Let's start off by putting 2 in between each set of atoms that we think is going to create a covalent bond. So let's put 2 in between the hydrogen and carbon, another 2 here, another 2 here to create a bond, and another 2 here. So then we step back and decide, did we accomplish 2 things? Did we use all 8 valence electrons? Yes, we did. Does each atom have what it needs to be stable? Does each hydrogen have 2 electrons at this point? Yes, they all do. And does the carbon have 8 valence electrons around it to achieve the valence octet? Absolutely. So this is a good Lewis structure. The next molecule that we're going to work on is quite simple. It's diatomic iodine. So a molecule of iodine has a total of 14 electrons because each iodine contributes 7. So we have a total of 14 valence electrons to distribute around this molecule. So let's connect those 2 iodines with a covalent bond. So there are 2 electrons being shared in the middle. At this point, we're going to take the remaining electrons and put them around the iodines as lone pairs. Let's decide if we've used all 14. We had the 2 in the middle, and then another 6 on the iodine on the left-hand side, and another 6 on the iodine on the right-hand side. That gives us a total of 14 valence electrons. Both iodines have 8 electrons total, which makes it stable. Our next molecule is ammonia, which has the formula NH3. We add up the valence electrons. The nitrogen has 5. And each hydrogen has 1, providing us with a total of 8 valence electrons to work with. We try to draw the structure as symmetrically as possible. We now start distributing those electrons where we believe there's a covalent bond. So 2 in between these atoms, 2 here, 2 here. We step back and look at what we've done. We've only used 6 valence electrons. We need to use 2 more. If you look carefully at the nitrogen, you'll notice there's only 6 electrons around it at this point. What if we put those extra 2 as a lone pair up on the top? I'm going to draw that as a cloud or like a balloon to show you that this is the lone pair on the nitrogen. Later on, we'll learn that lone pairs can affect the shape of a molecule, but for now, we just use them to make sure each atom is stable and has a valence octet. Our next molecule is C2H6. Adding up these valence electrons looks like this. There are 2 carbons, each with 4 valence electrons. There are 6 hydrogens, each with 1 valence electron. That adds up to a total of 14 valence electrons to work with. Now we know to put the hydrogens on the outsides, and we know to make it as symmetrical as possible. So why not distribute the hydrogens around the carbons like that? Start placing electrons in between the atoms to create covalent bonds. Now we look at our structure and see what we've done. Did we use all 14 valence electrons? Let's add it up. 2, 4, 6, 8, 10, 12, 14. Awesome. Does each atom have what it needs to be stable? Does each hydrogen have 2 electrons at this point? Yes, they do. Does each carbon have 8 electrons at this point? Awesome. That means this is a good Lewis structure. Our next molecule is CH2Cl2. We can add up the valence electrons. 4 come from the carbon. Each hydrogen contributes 1, and each chlorine contributes 7. So that gives us a total of 20 valence electrons. You might ask, how do I arrange these atoms? Let's put the carbon in the middle. Like we had mentioned earlier, carbon is less electronegative than the chlorine, and so he's more likely to be a central atom, and we know hydrogens go on the outside. So why not put the other chlorines over here? Start distributing electrons where we believe there's a covalent bond. And now we've used up a total of 8 out of the 20. But if you look at the chlorines, you can tell they're going to need some lone pairs on them because the chlorines will need 8 valence electrons by the time we're done. So we start distributing some lone pairs here. And now we step back and decide, did we use all 20 valence electrons? Let's count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's great. Does each atom have what they need to be stable? Do the hydrogens have 2 electrons each? Yes. Does the carbon have 8? Awesome. Does each chlorine have 8? Fantastic. This is a good Lewis structure, and we can move on. How about N2H4? Let's see what you can do with this. Valence electron-wise, each of the nitrogens contributes 5, and each hydrogen contributes 1 to give us a total of 14 valence electrons to work with. Again, since the hydrogens are on the outside, we're going to need to put the nitrogens in the middle, both as central atoms. Start distributing valence electrons. 2 between these 2 atoms to create a single covalent bond. They're sharing those 2. 2, 2, 2, and 2. Count them up. 2, 4, 6, 8, 10. Well, it seems like we're missing 4 valence electrons. Where else could they go? Well, if you look at the nitrogens, you can tell they are not stable at this point. They only have 6 valence electrons around them, and each could use 2 more. So it makes sense to put a lone pair on the top of this nitrogen and a lone pair on the top of that nitrogen. And now when you look at each atom, the nitrogens each have 8 and the hydrogens each have 2. We've created a stable Lewis structure. So I think it's time to get a little bit more fancy. Let's take diatomic oxygen this time. It looks like a really simple molecule, right? Counting up the valence electrons, there are 2 oxygens and each contributes 6, giving us a total of 12 valence electrons to work with. Let's put those oxygens side by side. Start putting electrons in where you believe there's a bond. And then we know that each oxygen needs a total of 8, so it would make sense to do something like this, right? How many valence electrons have we used? Count them up. 2, 4, 6, 8, 10, 12, 14. Wait a minute. We used way too many valence electrons. We only have 12 to work with. So the first thing I need to do is get rid of 2 of them. How about I take these 2 off the bottom? Now as I check out my structure, decide, does each oxygen have 8 valence electrons to be stable? Well, the oxygen on the left looks like it has 8. But whoa, the oxygen on the right, no way, he's only got 6. So what can we possibly do to make sure that both of our oxygens have the 8 electrons that they need for stability? Maybe we need to be a little bit more creative here. Do you see that lone pair that's on the bottom of the first oxygen? I'm going to try to move it. I'm going to take it away from the bottom. And what if I put that set of electrons in the middle? Whoa, what's going on? This is what we call a double bond. And I want you to notice that 4 electrons are being shared in between the 2 oxygens. To show you this a little bit more easily, how about I circle all the electrons? This oxygen has 8. The other oxygen also has 8. But when I draw it like this, you can notice that there really are 4 electrons being shared by both of those atoms. Sometimes chemists will do a simplified structure of this by using dashed lines to represent their bonds. And so a double bond would look something like that. Pretty cool. We now learned something new. We know that a double bond shares 4 electrons. In our next structure, let's deal with carbon dioxide. I think you're pretty familiar with that. Adding up valence electrons gives us 4 from the carbon, and each oxygen contributes 6, for a total of 16 valence electrons to distribute. We're going to put carbon in the middle. If you think about why, carbon is less electronegative than oxygen, so it makes more sense for him to go in the middle. Start distributing electrons. How about 2 here, 2 here, and then how about some lone pairs around those oxygens? Did I use all 16 valence electrons? I need to count them up. 2, 4, 6, 8, 10, 12, 14, 16. Great, I used all 16 of my valence electrons. What's that? There's something wrong with the carbon? Oh my goodness, you're right. The carbon only has 4 electrons around it, and it needs to have 8 for stability. Can you think of something that I could do to fix the problem? You're right. What if I moved these 2 valence electrons on the bottom and put them in between the molecules? And then this set of valence electrons, what if I moved them and put them here? Do you see what's going on? There's a double bond on the left, and there's a double bond on the right. So when we look at what each of these elements has, now this oxygen has 8, this carbon has 8, and this oxygen has 8 valence electrons as well. This looks like a really nice structure. We could simplify it by drawing it like this. 2 sticks for a double bond on the left, and also 2 sticks on the right for another double bond. You guys are doing awesome. Our next structure is C2F4. Adding up valence electrons. Each of those carbons contributes 4, and each of those fluorines contributes 7. That gives us a lot of electrons, people. We've got 36 valence electrons to contribute. Trying to make this as symmetrical as possible, how about we put 2 fluorines on each of the carbons, begin to put in electrons where we think a bond is going on. But now we've only used 2, 4, 6, 8, 10, and we realize there's another 26 that are remaining. So a quick look at the fluorine tells us that we're going to need a bunch of lone pairs around them. Okay, so the fluorines are looking pretty good, right? And we've now used up a total of 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34. Only 34 of our valence electrons have been used. So do you see where the flaw in the structure is? Look closely. Oh, each carbon only has 6 valence electrons around it. Can you figure out how to make them have 8? Right. What if we put those last 2 electrons in as a double bond? Now the fluorines have 8, the carbons have 8, and we've created a legit Lewis structure. Nice job. Our next molecule is CCl2O. So we've got 3 elements involved here. The carbon contributes 4 valence electrons. Each of those chlorines, 7, and then 6 from the oxygen gives us a total of 24 valence electrons to work with. The least electronegative element is carbon. Let's put him in the middle and distribute the rest of the atoms around it. Start placing electrons where you think there will be a covalent bond. And then let's start putting lone pairs in on some of these other elements that we know will need 8 valence electrons to be stable. So now let's count up how many valence electrons we've used. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We've used all 24 valence electrons. And now decide, does each atom in this structure have 8 valence electrons? Well, the chlorines look good, and the oxygen looks good, but oh no, not again. The carbon only has 6. Time to be creative. What can we do to give that carbon 8 electrons? We've already used all 24, so we can't add any more. So here's what I'm thinking, people. Let's take 2 off the bottom of this oxygen and move them over. What if we put them in between the carbon and the oxygen? So we've now got a double bond right there, and then a single bond between the carbon and the chlorine, and another single bond in between the carbon and the chlorine. And now we've got a really good Lewis structure. The next molecule that I want to do looks really simple, right? Nitrogen, which is a diatomic element. Each of these nitrogens has 5 valence electrons, giving us a total of 10 to work with. Let's connect them, and let's start putting some valence electrons in. Right, this looks good. Each of the nitrogens has 8. Okay, so I step back and I check things out. Count up the valence electrons that I've used. 2, 4, 6, 8, 10, 12, 14. Are you kidding me? This is not going to work at all. I've used way, way, way too many valence electrons. So I've got to go back and erase some of those. I've got to get rid of a total of 4. So now as I look at my structure, I've used 10 valence electrons. Does each nitrogen have what they need for stability? The nitrogen on the left has 8. That's great. But oh my gosh, look at the nitrogen on the right. That looks ridiculous. It only has 4 electrons around it. Time for a little bit of creativity. Could we move some of these electrons around to help out that nitrogen on the right? How about I remove these 2 on the bottom and move them to the middle? Well, now the nitrogen on the left has 8 and the nitrogen on the right has 6. I'm getting closer, but man, I'm still not there. How about I take 2 off the top of this nitrogen and move them in between as well? What in the world is that? 6 electrons being shared between the nitrogens? Yep, you can do that, people. This is called a triple bond. It's legit. Those 6 electrons are being shared by both of the nitrogens. If I did that circly-dirkle thing, I can show that this nitrogen has 8 and this nitrogen has 8. And so this is what's called a triple bond, and sometimes we show that by putting 3 sticks in between the 2 atoms. This is so cool. We learned something, again, that's new to us. What if we tried to do acetylene, which is C2H2? For our valence electrons, each carbon contributes 4, and each hydrogen contributes 1, for a total of 10 valence electrons to distribute. Trying to make this as symmetrical as possible, I begin to put electrons in where I think covalent bonds will take place. Okay, but I've only used 6. At this point, the hydrogens look like they're stable. They have 2, so I can't put any more around the hydrogens. So let's think creatively here, right? Each carbon right now only has 4 valence electrons, and I still need to use up 4 more from my total of 10. I'm going to try something. What if I put a double bond? Now I've used up 8 of those 10. Each carbon at this point has 6. Okay, I'm getting closer. Can you see what's about to happen? How about those final 2 I also put in the middle? And we've got a triple bond in between those 2 carbons. And now each hydrogen has 2, each carbon has 8, and we've used up our 10 valence electrons. If we wanted to do a simplified model, we could use the sticks to show the single bonds on the right and the left, and then the triple bond in the middle. So do you have time for one last structure? Let's try HCN. Hydrogen contributes 1 valence electron, carbon 4, nitrogen 5, giving us a total of 10 valence electrons. Let's put the hydrogen on the outside, carbon in the middle, because it's the least electronegative of the 2 atoms that remain, carbon and nitrogen. Start putting electrons in where we believe there might be bonds, and then maybe use up those other valence electrons. And so I've put down a total of 10. I'm feeling pretty good about this, right? I see a mistake. Can you see the mistake? Hydrogen looks good, nitrogen looks good, but oh, that poor carbon in the middle only has 4 valence electrons. How about we start shifting some electrons around? Could we take 2 from below the nitrogen and move them to the middle? Does that look better? Now the carbon has 6. Ooh, we're getting closer. What if we take 2 off the top of the nitrogen and put them in the middle? How's that look? Carbon has 8, nitrogen has 8, hydrogen has 2. Ooh, I'm feeling really good. Let's make a simplified model using the sticks, and it looks something like this. A single covalent bond on the left, a triple covalent bond on the right. This now concludes our lesson on Lewis structures. I hope at this point you're really good at adding up your valence electrons and trying to distribute them using single, double, and triple covalent bonds. Thanks for joining me.